Good morning, everyone, and thank you very much, Christiana. I am delighted to be here with you. Indeed, I was so much looking forward to being Anvers this morning that I chose an appropriate screen as well. So I want to talk a little bit about AI. Everybody's talking about AI. I would say we are part of the design automation and design communities, and I would like to discuss with you what is in it for us. So let's take an overview here of what's going on in artificial intelligence, and in particular in neural networks. This plot shows the complexity of neural network model descriptions over the years. Pre the use of during the 80s and 90s and the 2010s, people were using CPUs to compute and train neural network models. And as a result, the complexity of this model was pretty much constant. The complexity of a LeNet that came out in 1988 is pretty much the same of the winner of the ImageNet classification in 2020, which was the very first year of that ImageNet competition. In 2012, AlexNet was proposed by researchers in Washington, I think. And it was the very first time that people were adopting the use of GPUs to compute and train neural network models. Because of the additional capacities of GPU, it became possible to have much more complex models and model description than it was before. So as a result, AlexNet was a 56 million parameters type of neural network. And then around the 2015, 2016, specialized hardware accelerators for AI emerged. And that really opened the floodgates for faster and faster model increase in model descriptions. Indeed, I would claim to say that even in my plot is a logarithmic scale plot, there is really a double exponential. The growth in the past 6 years, in terms of model complexity that have been proposed for neural network has been super linear. There are models like the Woodhouse 2.0 that is trained to do natural language processing both in Chinese and in English. Now, one of the questions that people may ask at this stage is, but do we have a hardware acceleration for AI because the models are so complex, or the complexity of the model has promoted the development of hardware acceleration? I don't know if it's a chicken or the egg first, but definitely they're feeding into each other and one is enabling the other. Not only models are becoming of increasing complexity, but also there is an increasing amount of funding that venture capitalists are dedicating to hardware acceleration startups in artificial intelligence. And this is a recent plot. It's updated as of January of this year of the funding that has been invested by venture capitalists in a number of startups that do AI acceleration. It ranges from 5 million to over $1 billion. And indeed, that company, Sambanova, was co-founded by my PhD advisor. I do remember that when I graduated with my PhD, on my way out of the door, he told me he had a startup at that time. He had a hardware design startup at the time. And he told me, remind me not to ever do a hardware startup ever again. And now he's back at that. Although I have to say now he has 1 billion reasons to invest again his time and effort in a hardware startup. And then demonstration of how critical and how pervasive neural networks and AI have been, the energy that we spent worldwide for training this neural network is mind-blowing. It has been estimated that the energy spent in training neural network doubles about every 3.5 months. And as a little example, that model GPT-3, which came out in 2020, it's 175 billion parameters, and it is estimated to take 314,000 exaflops to train. So if we were to run that on a GPU V100, that would take about 28,000 days to train. Of course, you can parallelize a workload, and you can do it much faster if you have many, many GPUs. But the bottom line is that it is estimated that it takes 190,000 watt hours to train the model, which for typical energy source in the United States will correspond to about 85 tons of carbon emissions. That's the same type of emission equivalent to driving 700,000 kilometers, basically like going from Earth to the moon and back. And not only that, a recent report by two consortia in the United States, the Semiconductor Industry Association and the Semiconductor Research Corporation, indicated as a seismic shift the use of energy for computing. And they have estimated that the amount of energy required for computing is growing exponentially every year. And it will quickly have to flatten because it's approaching the world energy production, the energy production worldwide. And so because there are still other activities that people spend their energy in, like creating food, for instance, the amount of energy left for computing is decreasing. It will have to decrease. Okay, so AI is enabling wonderful opportunities. Because of AI, now we have complex systems that can interpret language. I mentioned earlier on the Woodhouse 2.0 model. That model can generate an image from a language description, can label images, can generate essays, can write poetry, and can do so in 2 different languages. And this is just an example. We have very fine-grained image recognition. We have complex recommendation systems that are extremely sensitive. One of the key things that changed when the AlexNet model came out is not only that the model was more complex, but the accuracy of the model prediction went from a 75% to an 85%. So, as I said, AI is enabling wonderful opportunities for society and for everybody on the planet. But how do we, our community, continue to enable AI? As I showed, there are several roadblocks that indicate that pretty soon it will be impossible to sustain the evolution and the growth that AI has enjoyed in the last 6 to 8 years. And that will span the energy that is needed, the storage that is needed to store this model, and the computation needs for that. So all of this space, I think, opens a lot of research opportunity for our community, for the design and EDA community. I'm going to spend the rest of my presentation outlining some of these research opportunities within the directions that I think are critical for enabling AI computations. And so here we have some ideas that came from the Application Driving Architecture Research Center, also called ADA, inspired by Ada Lovelace, one of the first computer scientists in the planet in history. So the ADA Center, which I direct at the University of Michigan, is a 5-year endeavor. It started at the beginning of 2018 and it will end at the end of 2022. It comprises a team of 21 faculty members from multiple institutions in the United States and 130 graduate students, PhD, mostly PhD and some master students. It's co-sponsored by SRC and a consortium of semiconductor companies and DARPA. And these are all the research that are part of our center. They are affiliated with 10 different institutions in the United States, from Harvard to MIT, to Princeton, to University of Michigan, to University of Washington, and to University of Illinois at Urbana-Champaign and Georgia Tech. So what's the goal of the ADA Research Center? Well, the ADA Research Center goal is to reignite computing system innovation by developing new architecture and technology for value creation, and by developing and proposing fast and accessible design flows that would enable a much researcher to explore new computing solutions. And we've done this for several years. We developed lots of new architecture acceleration, embracing of new devices, and propose solutions for compilation flow from domain-specific languages to hardware. However, in the last year or two, we have started to explore the impact that the trends outlined in the AI community have potentially had within design and hardware. So first of all, it is now clear, and the pandemic made it super clear, that we have entered the data flood area, where the amount of data we produce is far outpaces the ability we have to compute with that data and transform the data into information. In addition, as everyone communicates more and more electronically, privacy and data security has become a growing challenge. And believe me, I come from a small town in Italy, and privacy was an issue long before the digital age. And finally, our planet is on fire. We're going to discuss a little bit, I'm sure you all know about it, but we'll discuss a little bit what are the implications of that on computing. So let's talk first of all of how can we possibly tame this huge data flood that is coming our way. As I said, we have entered the data flood area, and COVID was a great accelerator in that space. During 2021, 79 zettabytes of data have been produced. The year before it was 2 zettabytes, but the year before there was no COVID, or only partially there was COVID, and people were still adjusting. Also, it is estimated that 2030, 90% of people age 6 and above will be digitally active. That's a vast fraction of the population, which is estimated to be about 8 billion. And then in addition to individuals who are connected and be digitally active, we also have a flood of Internet of Things. We estimate by 2025 there will be 75 billion Internet of Things devices that are connected. And then in addition to that, there is an economy online, as you all know. The estimate is that individuals spend over $1 million a minute on commodity purchases on the Internet. Unfortunately, over 99% of the data that we produce and store is called dark data. It means it's never analyzed, it's basically valueless because of that. And it's simply because we don't have enough compute ability to process all that data. And so what are we doing about it? Well, some of the solutions that have been explored in the ADA Research Center span accelerating computation so that we can process more data, having more efficient storage, and having compute near the data storage rather than create a lot of communication to move data to process it. So the first solution I was going to outline is this Omega accelerator that accelerate the computation for natural graphs, basically graphs that arise in regular in real world situations. We actually done a study early on that indicates that the majority of natural graphs have a small set of vertices that are very highly connected, almost like a click, and then a very long tail of loosely connected vertices. And so based on this idea, what we thought is if we could do very fast computation and very fast access to this core of highly connected vertices, we could actually speed up the computation on the entire graph. And that's the idea behind the Omega solution, where we deployed a scratchpad by retrieving some of the storage that was dedicated to the cache. And this scratchpad just stores the most connected vertices in the entire graph. And what we found is that on average, we attain an over 2x improvement in performance, and we have a significant memory reduction because of course the communication to lower level caches and memory is reduced, and almost no hardware overhead. And the reason there is almost no area overhead is because the scratchpad doesn't have all the multi-ways of access that the caches do. Another solution developed within the center is by researcher Ritu Das, who developed a solution called duality cache, where the last level cache in a 18-core multi-core processor is reorganized to operate also as a highly parallel ALU. Indeed, she can basically add a little bit of logic next to each slice of the last level cache to obtain almost 1.5 million serial bit line ALUs that can be used to do computation on the data stored in the cache without transferring it to the CPUs. And so as a result of this work on a number of benchmarks, both from Rodinia and OpenACC, she was able to obtain a 4x improvement over running the same benchmark on a GPU, or 72x improvement 72 times improvement over a CPU. The energy reduction is 20 times for CPUs and 6 times for GPUs. And this is as a minimal area overhead, basically just the area overhead of putting the bit line ALUs, which boils down to about 3.5%. And another solution developed within the center by Zach Tatlock is called dynamic tensor rematerialization. The idea is that neural network models are so complex and they have a lot of tensor weights. And so what Zach proposed to do, instead of trying to access all of them and store them in cache as much as possible and the slow access memory for the remainder, it can generate them on the fly. So it can only store a small portion of the tensors, and then it can recompute the stale tensor on demand without accessing the memory. And this has led to significant improvement in the overall performance of the computation, because it can avoid transferring data and instead basically identify a compressed way to store the data. Another direction that we discuss as being a critical one if we want to improve the space on neural network is in enabling data privacy. So why do we need data privacy? Well, data security is now very secure today. There are a growing number, an exponentially growing number of software vulnerabilities that are discovered almost every day. And as we fix one vulnerability, new software is produced, new vulnerabilities are also released with the software. So the truth is that it most likely all software is eventually hackable. There is no software that can be completely secured. No practical software that can be completely secure. And then in addition to that, there are always a wide range of side channels. In the olden days, the side channels would require having some voltage monitoring or current monitoring. Now there are architectural side channels where I can derive side channel from monitoring the activity on the cache or the time into the computation in clock cycle. And so this side channel can actually be deployed in software alongside the software that I'm trying to attack. And so what are we doing about that within the center? You know, of course, you can only imagine that this complex model, not only for their training, but even for their classification, manage a very large amount of data that may have different needs in terms of security and privacy, maybe because they are personal to an individual, or maybe because they are related to medical data or financial data. And being able to secure the access to that data is a critical aspect to promote the continuous adoption of AI. So one of the solutions, solutions that have been proposed in the center are based on the idea that if I cannot trust software, I need to keep data always encrypted in software. I can only trust hardware for doing the computation and for unencrypted the data and seeing the data in the clear. So if I had a solution like that, where data comes in encrypted to an hardware module and lives encrypted, a software hacking technique will be able to possibly steal the data, but would only steal encrypted data, which is valueless. So there are some solutions that have been embracing and exploring this direction. One is homomorphic encryption, which in its native state is between 500 and 1 million times lower than native computation. So basically comes with a very high price, but it can provide guaranteed data privacy. And the other is sequester encryption, which has been proposed within the center and claims to, in most cases achieves no more than a 2x slowdown. So what is sequester encryption? The idea of sequester encryption is that I'm going to have a main CPU core and an enclave, which is not storage enclave, it's an ALU enclave. Data is encrypted by the client in its CPU client side, and then transferred to the SAU enclave encrypted. The enclave can be the data center, for instance. Within the enclave, it gets decrypted, computed, re-encrypted, and then transfer back to the main core. So as a result, the data center server, the transfer servers, nobody sees this data in the clear. It's only the clear inside the EU enclave. With this approach to computation, there can be no software vulnerability or timing side channel. Indeed, the EU enclave is designed so that it doesn't expose any timing side channel. And since only the SAU, the sequester encryption LU is trusted, no other hardware or software in the system can be trusted, need to be trusted. Another researcher in the research center embraced homomorphic encryption, and what he did is he identified ways to accelerate homomorphic encryption. Basically identified that if we can rely on deep pipelines to do the dot product computation of homomorphic encryption, and we can put enough hardware resources into that effort, then we can actually accelerate deep learning inference computation, right? Basically the key mechanism of what happens in AI computations. And then he found that in this solution called Cheetah can actually get within 2x of a plain text inference. So it's 2x slowdown compared to a solution that doesn't use homomorphic encryption, that's the same type of computation, a neural network inference, and is 5,000 times faster than running homomorphic encryption on a generic CPU. And this is actually a project that is also part of a DARPA program called DATE2022, whose goal is to attain a slowdown in homomorphic encryption computation that is less than 10x the one on plain text native computation. Then we talked about our planet being on fire. What does it mean, and what does it mean for computing? Well, as you may already know, the Intergovernmental Panel on Climate Change has identified a target goal of 1.5 degrees of global warming above pre-industrial level, meaning the 1800, in order to avoid drastic impact on humanities due to climate change. And when you say drastic impact, it means hundreds of millions of people that would be thrown into poverty or would experience disasters. And so in order to achieve that goal of staying within 1.5 degrees of global warming, the overall global emissions caused by humans should be decreased by 45% by 2010, 45% of 2010, and emissions should be a net zero by 2050. Notice that in 2017, only 70% of electricity came from renewable sources, and so all the rest of the electricity produced in the world actually was connected with carbon emissions and greenhouse gases emissions. Now, let's look at computing. What are the impacts of that in computing? Well, in the United States, it is estimated that the electricity production contributes to 25% of the emissions of the country. And within that, it is also estimated that ICT, basically information and communication technology solutions, use about 20% of all the electricity. Although I would like to really show you on that plot, it's 20% today, and it looks to be over 3 times that, or over 2 times that by 2028. Twice that, 2028. So it's a very volatile number that, you know, of course, if these neural network models are growing so quickly, the amount of energy spent in ICT is growing also very quickly. So it appears that today it could be about 5%, 5 to 10% is of global energy spent in computing, but that could quickly grow to a very significant fraction of the worldwide energy consumption. And again, I would like to bring back the estimate from the Semiconductor Industry Association and Research Corporation, who suggests that by 2030, we're going to be limiting the amount of computing because the amount of energy spent in computing is approaching the energy production, the worldwide energy production. So the motivation for that plot was actually identify a way to do computing that are much lower energy, but we can also see the trend from there and the estimated trend from another source that represent many of the semiconductor companies out there. as a result of these trends, and as a result of the importance that greenhouse gases emissions and climate change is having, many technology companies have made pledges for themselves. A number of them are promising to be carbon-free or greenhouse emission-free by 2030. Some actually have even earlier timelines. For instance, Meta claims to be carbon-free already since 2020 for scope 1 and 2, and will be also carbon-free by 2030 for scope 3. Now, what are all these scopes? This is a little review of the scopes. So what does a computing carbon footprint come from? There are two types of emissions related to computing. One is related to the energy that is consumed to do the computation as we run different applications. And the other is related to the emission related to the manufacturing of hardware that constitute the computing platform. So for instance, if we were to have a company, as an example like Meta, the scope 1 emission are the one due to Meta's own activities. For the most part, that's running the data center. So the refrigerant for the data center, the diesel and gas for running the data center, and the cooling of the facilities, and the transport owned by Meta. Scope 2 are the emission related to the production of energy they purchase. So if they purchase electricity, and that electricity is from a hydroelectric source, then that's carbon neutral. But if the electricity is produced by using methane, for instance, then there are emissions associated with that. And then there are scope 3 emissions, the ones that, if you remember, Meta commits to be neutral about by 2030. And so the scope 3 emissions are the one associated with my customers and my providers. So my providers will be the companies that produce the hardware and the racks, and they build the data center, and they do and they service my travel needs. And the downstream will be the emission related to my customers using my services. So for instance, when you are on Facebook and you do transactions or message people on Facebook, you're burning energy, and that's part of Meta downstream scope 3 emissions. And then recently people have identified scope 4 emission, which I think is actually a very positive note on this whole universe. Scope 4 emission are avoided emissions. So for instance, Zoom, who has developed a software that allows many individuals not to travel, like I'm not traveling today, has a significant scope 4 avoided emissions, because all the travel that doesn't happen because we can use Zoom is actually an avoided emission. And so that's you want to have as many scope 4 emissions as possible in your activities. Now, Meta is a company whose emissions are mostly associated with running data centers, right? And so in the case of a data center, the scope 2 emissions tend to be associated with operating the system, and the scope 1 and 3 emissions tend to be associated with capital investments in setting up the company. So the purchase of the hardware is a critical thing here. Okay, so we've been talking about data centers. Are the data centers the big culprit? No, really not anymore. This is a slide from a conference in 2008, which suggests that data centers worldwide had carbon emissions that were equivalent or very close to the total emission of the country of Nigeria and that of the Czech Republic. But since then, the ability of data center to be effective in the use of their power, basically using the power they consume specifically for computation, not for cooling or for other activities, has improved significantly, such as today, their PUE is very close to 1. So that means that the vast majority of the energy that they use is useful energy used in doing computing. What about the rest of the computing flow? You know, what about the fabs that produce the hardware? I see there as a place with lots of opportunity. Carbon emissions related with mobiles and mobile system have a wide range, both from running the application to the hardware of producing them. We'll look at that in a second. There are opportunities for optimizing how applications are computed. Optimizing in location, is it better to keep it on my smartphone, or is it better to move it to the data center where the energy to do the computation could be renewable or from a natural source? And what about the cost of the data transfer? What about the timing of the computation? How can I compute at a time where there are more natural resources available for energies versus now? And then the fabrication of silicon chips. In an estimate by my colleague David Brooks, on average, for a typical application, 30% of the emissions are associated with the production and manufacturing of the silicon chip associated with that computation. And so that was not the case several years ago, but because of these many improvements on the energy that is used to do computation, the fraction that is now relying on or due to the manufacturing of the silicon chip is becoming increasingly high. And to show you this is a plot of different generation of smartphones from Apple, Google, Huawei from 2015 to 2019. And what we're plotting here is the performance of this smartphone on the x-axis, and the performance is evaluated of number of images that can be classified every second versus the carbon footprint of the components on that smartphone. And that has been done by David Brooks from Harvard and his students by analyzing the components of each of those smartphones. And so what we can see is that back in 2016, if I were to do the Pareto curve of the smartphone produced that year or prior, it was a fairly flat Pareto curve in manufacturing carbon footprint with an improving performance. And then in 2017, the iPhone X came out, and my Pareto curve actually turned up quite a bit. In 2018, there was a new product that allows us to go back flat on the Pareto curve. And then in 2019, we added several new phones that also had an increase in carbon footprint. And so the overall message of this plot is to say, you know, over the past 4 to 5 years, there have been significant improvements. You know, we went from less than 10 to almost 80 images per second classified. So a significant improvement in the performance of the smartphone. However, that significant improvement came with a non-negative increase in carbon footprint. Some were a small increase, some were a significant increase, but we still have to see a product that that can improve performance while also improving or reducing the carbon footprint of the manufacturing process. And so just to give you an example, there is a phone highlighted there from 2019, the Pixel 3. And based on the manufacturing footprint of that Pixel 3, which is 45 kilograms of CO2, it would take 3 years of AI inference, of pretty much image classification, some other neural network model inference, to produce as many emissions as the manufacturing, as the ones that were associated with this manufacturing. So in a sense, I would amortize, or at least I reach a ratio of 1 to 1 if I use that for doing image classification around the clock for 3 years. And then after that, it will, you know, the use will start being associated with more emission than the production. However, probably that's true for most of us. We switch smartphones within 3 years, or around the 3. On average, people switch around the 3-year mark. And so, you know, the only way to address this would be to actually have smartphones that have a longer lifespan, because otherwise the production costs are always the preponderant aspect of the emissions. One of the projects that my colleague David Brooks exploring this space, and this is an ISCA paper that is coming out this summer, is a modeler, an architectural modeler for carbon emissions, which takes into account the characteristic of the fab, the energy sources that are used and how carbon neutral those sources are, the software application that have to run on a system, the hardware design, and the needs, and it can do computation separately for the operational emission, the one associated with running the application, and the embodied emission, the one associated with manufacturing the product. And then from there, it would be possible to start making optimization in the system that are aware of the sustainability aspects. And so they created this complex model that is actually, they're releasing and making publicly available, that take into account all these aspects with a number of parameters, and it's able to estimate the emission associated with a specific computing system and application with that. Another approach that, as a byproduct, is valuable for the environmental aspects of computing is chiplet-based design. And indeed, DARPA had a program in this space that is just closing. It started, I believe, in 2018. And so the idea is that how can we design systems that are no longer monolithic silicon, but actually use different chiplets. And then at that point, it would be possible to mix together newer generation chiplet with older generation chiplet, and the composability and flexibility would allow possibly also longer lifespan for a certain product, thus allowing to amortize the emission associated with this design over multiple generations, but also allow to reuse maybe older generation components that already been used in the past when they were frontier of the technology, and still make valuable use, basically extending their lifetime we were discussing before. And so within my group, we have worked on a couple of solutions in that space. One is this SIP interposer, basically a flexible and configurable passive interposer that allows to combine chiplet of different dimension and with different communication need on the same ASIC, on the same system in package. And then Chopin, which is much more of a evaluation or estimation tool that provides guidelines allowing to estimate what's a proper area that is viable for a chiplet type of solution, even taking into account the reliability of these components, and also what's a proper complexity. Very small components is not worth having in a chiplet. Too complex of the components, we're moving to the ASIC, so it kind of does this trade-off based on the number of parts that are needed and the size of these units. So to conclude, we identify some ideas and multiple opportunities in these three domains, which are all critical to continue to enable the AI evolution and to unlock the roadblocks that are emerging in computing with neural networks. So on the front of the data flood, opportunities are in identifying new memory devices that are more compact, maybe use less energy, maybe they can store multiple bits. The ability to leverage software and compute power to offset the storage that we have available. And then also, you know, we probably all know about PIM and computing memory type of solution, which cut the whole cost of communication from the equation. On the privacy front, you know, exploring solution in privacy-aware storage is a fantastic direction, especially given the GDPR regulations in Europe, and also the ability to enhance data with metadata that indicate what are the privacy needs for a certain block of data. And on the sustainability front, they need to optimize computation for carbon emissions, exploring reduce and recycle solution for computation, where a use, for instance, could be through this chiplet-based design. Reduce would be to think about architectural solution that maybe rely on some more flexible hardware, so I can manufacture once and map multiple hardware solution. FPGA have been around for a long time, maybe other solutions that have a coarser granularity so that they don't pay the same price in terms of performance. And then emission optimized type of computation in terms of localizing where the computation happened, being able to bring that up at the programming level, and timing when the computation happened. And to conclude, these are the sponsors for the research center, and also they're part of the SRC sponsors. And they come together all in the JUMP program that sponsors the ADA Research Center. So thank you very much.